So we're moving on to the second part of chapter 32. And so let's start right away with a question. We know a little bit about how the magnetic field from a wire works. So taking our knowledge of this, suppose we take a wire and make it into a loop, like in this picture here. What direction would the magnetic field be at point A? So use your right-hand rule, see what you come up with, and we'll talk about this. Okay, so the answer I get is it'll be pointing out of the page. So let's take a look at this. So here's our loop. Now we take our curly right hand rule. If I look at the bottom and I put my thumb along with the current from the bottom, okay, in the middle of the square, my fingers are pointing out of the page, and then they'll be pointing into the page on the other side. All right, if I look at the right side, I see the same thing. Okay, into the page, out of the page. The left side, I get the same thing, and then finally the top, I get the same thing. So you see that the wire has a tendency for the field to be coming out of the page in the case where it is here, where it's going counterclockwise. So where the current is going counterclockwise, the magnetic field is coming out of the page. So hopefully that's what you got. Points out of the loop, and we can use our curly right hand rule to figure this out. And so here's a picture of a loop. So generally when they have loops, they'll make them little circular loops. And if you look at these two loops, it's the same sort of idea. Okay, so if on the right-hand picture, the current is going counterclockwise, and inside the loop, the magnetic field is coming out of it. All right, and if you look, there's a side picture, it's the same sort of idea. You can use your right-hand rule to get that association. So we're going to deal with these loops. And here's the right-hand rule for dealing with loops. So the first one is basically doing the way we just did it. So you point your thumb in the direction of the current, and then see which way your fingers point through the loop. And that's totally fine. If that makes sense to you, do it that way. Another way to think about it that can be a little bit quicker is sort of switching up your fingers and your thumb. And so curl the fingers of your right hand around the loop, and then your thumb is pointing in the direction of the B field. So if we go back to that loop we were doing, if I take my fingers and make them go in a counterclockwise direction, my thumb points out of the page, out of the screen, and that's exactly which way the B field points. If I look at this loop here on the right, if I put my fingers in the direction of the loop, my thumb points out of the page. I usually generally do this way. It's another right-hand rule to remember, but I think it's a little bit easier. And so here's a picture of a current loop and comparing it with a permanent magnet. And actually the lines look pretty similar. Okay, so what we do is we actually will call the North Pole this side over here, and the South Pole this side over here. All right, and so when I do this with my right hand rule, my thumb is sort of pointing where the North Pole is. And so here's an example for you guys to give it a try. So here we have a little loop. It's coming out of the page on the right and going into the page on the left. The current is. I want to know is which side of the current loop is the North Pole of this little magnet. So give us a try and let's tell us what you think. All right, so hopefully you got that it's the bottom side. So if I do my right hand rule again, if I put my fingers in the direction of the current, which is coming out of the page and going into the page, my hand is sort of situated so my thumb points down. And so in this picture here, the north side of this magnet would be here and the south side would be here. So you really want to stress this idea that when you have a current loop, it's like you have a little tiny permanent magnet. Okay, so currents and magnets produce a lot of the same results. Here's another example, kind of doing the opposite. Here we have the magnetic field lines. I want to know is what direction do you think the current would be in this loop, and then which side would the North Pole be? So give this a try and let's see what you think. Okay, so here I get this answer. So if I put so I'm using the second right hand rule. I put my thumb in the direction of the magnetic field line so it's pointing down. My fingers tend to go counterclockwise around this loop. All right, and because of that, where my thumb is on the down side, the bottom side, so that's where the north would be. So again, the north would be down here at the bottom side of this, over here, and the south would be over here. This is really tricky, especially in a video. Give these a try and see what you come up with, and of course we'll do over some more examples in class. Here's another little picture of the same setup. They like to show these little pictures in the book, like on the right, where they have little iron fillings, and basically those are like little compass needles, and they line up with the magnetic field around it. So it's kind of showing you that it really is, the magnetic field really does look like that. One last comment about these loops. So you can call a loop of wire like this, we call this a magnetic dipole. And so we dealt with this before when we did electric dipole. An electric dipole was a positive and a negative hanging out together. Well, now if you have a wire loop, okay, like so, and suppose this is the north side and this is the south side, that's what you have. You have the north and the south. It's very analogous to having plus and minus. Okay, and so we call this the dipole. This will come up again. We won't deal with it too much right now, but one important definition is there's a definition of the magnetic dipole. And it's simply the area of the loop, so whatever the area would be here, so you find the area of that, this would be pi r squared or something, times the current in the loop. All right, and then the vector points from the south pole to the north pole. So in this case here, if I take my fingers around with the current, my thumb would be pointing upwards. And so this would be kind of my north side, this would be my south side, and so the direction of it would be pointing this way. In this picture, the direction would again be pointing this way. Okay, so that's a definition, and we'll pick up this definition again later at